In this video, I'd like to continue talking about taking roots of complex numbers. And we have this equation where z, our complex number, is raised to the third power, and this is equal to negative 64. Now, because this is raised to the third power, there are three distinct solutions, and they tell us one of the solutions is negative 4, since if we take negative 4 and raise that to the third power, two of the negatives cancel, but one of them does not pair up, so our answer is negative, and 4 to the third power is 64. So this, we can prove to ourselves, is negative 64. It does solve this equation, but the other two solutions are complex numbers. And the general strategy is to rewrite both sides of the equation in either polar form or exponential form, though writing it in exponential form tends to be faster. And remember that the complex number z is equal to the magnitude of z multiplied by e to the I times theta, where theta is the angle of the number measured relative to the positive real number axes. And this part right here, we can use Euler's formula. This is equal to the cosine of the angle plus I times by the sine of the angle. This exponential form is really just a more compact polar form. And we will raise our complex number z to the third power, and we will write minus 64 as a complex number in its polar form, though this would have an angle. If we plot it on the complex plane, negative 64, this would have an angle of minus 180 or positive 180. Or we can do it in radians. This would be pi radians. So any of those representations work, but let's start by rewriting everything. We would have z, which in its exponential form is its magnitude, multiplied by e to the I times theta, and we're raising it to the third power. And over here, we have a complex number where its magnitude, remember, is a positive number, so that's 64. And its angle, we know, is 180 degrees. Now, we need to be careful with the angle, since if we add 360 degrees, we end up back where we started. So we can add multiples of 360. We can add it as many times as we want, and we will represent that as 360 times k, where k can be any integer, but we really just need the first three, including 0, where if we do add in more than this, we will actually just get duplicate solutions. So whatever exponent you're raising it to, that's how many of these k values you would actually need here. So for this equation to be true, after we simplify the left-hand side, the magnitudes must be equal and the angles must be equal. So let's first simplify. We are raising this to the third power, and we can rewrite this as the magnitude of z to the third multiplied by this exponential expression raised to the third. And since we are raising an exponent to an exponent, we multiply the two exponents. And this is all equal to the the right-hand side over here. And like I mentioned, for this to be true, the magnitudes must be equal and the angles must be equal. So 3 theta must be equal to 180 degrees plus 360 degrees times by k. And we will solve both of those equations to figure out the angle and the magnitude. And let's start with the magnitude. We essentially just need to take a cubed root of each side, or we can raise each side of the equation to the 1/3 power to cancel out the cube. And what we will find is that the magnitude is equal to 4. So each of our solutions will have a magnitude of 4, but they will have a different angle. And we can see that's true by looking at the answer choices. They each have a magnitude of 4. Now to find the angles, we solve for theta, so we will divide each side by 3. And we will get 60 degrees plus 120 degrees multiplied by k. And now to find the different solutions, we we'll just plug in different values of k to find the three solutions that we're looking for. And if we plug in k is equal to 0, which we can call theta 0, we get 60 plus 0, so 60 degrees is a solution. If we plug in 1 for k, then we get 60 plus 120, which is 180 degrees. And if we plug in 2 for k, this is 240 plus 60 would give us 300 degrees. And for all of these, the magnitude is 4. And what we can notice is that this solution right here is actually our given solution, z is equal to -4. Since a number in its polar form that has a magnitude of 4 in a direction of 180 degrees, if we plot that on our complex plane here, and let's say we have 4 tick marks, that would be this number right here, which you can see is -4 on the real axis. It has an angle of 180 and it is a distance of 4 away from the origin. Now, the other two numbers, we can plot those if we want, and this is not going to be drawn to scale, but we can get a good idea of how the symmetry looks. We have a 60-degree angle, and it also has a magnitude of 4, so that will be somewhere around there. And we have a 300-degree angle, which would be somewhere down here, and that would also have a magnitude of 4. And the symmetry is that if we were to draw a circle, each of these points would be on that circle, and you can see it's not drawn perfectly to scale. This should be right about there. But the radius of this circle is the magnitude of each of our solutions. In this case, it is 4. And you can see they are evenly distributed. There is symmetry around this circle here about the origin. And that should always be true with your roots in an equation like this. Now, to find our solutions, they're all written in polar form. We know their magnitude needs to be 4, and they have an angle of 60 degrees and an angle of 300. And if we want, we can check these by actually taking our solutions and raising them to the third power. So we take the magnitude, raise that to the third power, we get 64. And then when taking our direction and raising that to an exponent, we multiply the angle by whatever that exponent is. And 60 times 3, that is 180. So we have 64 for the magnitude and an angle of 180, which would give us -64. And likewise, we would end up with the same value when raising this expression to the third power. We would also get -64, and I will leave that as an exercise to the viewer.